Hello everyone. Today I'll be talking to you about the routing and shortest path algorithms. I was gonna talk to you regarding the shortest path algorithm, but students need to understand where does the shortest path algorithm has been used. There are a lot of different cases, especially it has been applied to routing mostly. My name is Tama. I'm professor and Student Initiative Innovation Director at Rochester Institute of Technology. So let's get started. So I want to talk to you about the network layer and the static routing, the source routing, flooding, and the Dijkstra algorithm and the Bellman-Ford algorithm. In the Dijkstra and Bellman-Ford shortest path algorithm is very famous for that. And I want you to know that there are, several different routing, shortest path, not the shortest path existed. So typically what happened is, in a network layer, the layer three, the routing, that's where the location shortest path, is being used, as you hear. So there's congestion control, connection control. One thing about the network layer is that controls from end to end, source to the destination. And that's why you need to, not the network layer needs to find the way, get to the destination, right? So network layer is very, very important. So that's why you need a shortest path algorithm there. That's what it has been used. But considering the QoS, quality of service, there are different weights applied to it, not just the shortest. Shortest does not mean the a packet will be delivered, quickly, because when everybody take that certain road, for example, right? There's Gangnam, there's a certain road, it's very, very congested around 5 o'clock. So it doesn't matter how short it is, it's even though it's a short destination, it takes a long time to get there, right? So distributing the route is very important. So what we call as a QoS routing, quality service routing, is it considers congestions and also the how many packets on the path and things like that. Right now, GPS, for example, Google has GPS, it considers how many cars on the road, which particular road, whether it's being congested. It provides ways around, right? So that's what is being used. So when you think about the data link layer, it's a point-to-point. We don't really need routing in this area. It's a point-to-point, one point to another. So you don't need a routing. You don't need a shortest path algorithm for that. So physical layer is it's a point-to-point as well. It can be more in the wired and the wireless scenarios. Okay. So for network layer uses the services of a data link layer in a reliable point-to-point, and it's all the point-to-points are put together becomes a route. So we add a packet switching end-to-end connectivity. So shortest path algorithm, traditionally has been used in the networking. Then later on, the user in the vehicle, what do you call the vehicle routing as well. But right now, in the vehicle routing, if you use the shortest path in New York City, for example, it might not be the best because congestion is really pretty bad in New York City, probably more than Seoul area. So we really need to be able to distribute the vehicles so that the congestions are spread out. So that's a different story. So provides end-to-end delivery of packet as a service to higher transfer layer. Can offer connectionless or connection-oriented services and establish and manage connection through subnets. Okay. So it determines route from packet from sender to the destination is beginning to end. Okay. Beginning to end. Typically shortest path algorithm used in the beginning to end. Okay. So the path, whatever the path is needed in a vehicle, it could be the drone, or it could be the networking or whatever. It's it's beginning to end. Exercise congestion control to maintain network efficiency, allow transport layer to send data from host to host. Transport layer is different from network layer. Network layer is how to get there. And transport layer is about whether it has arrived safely or not. If it has, if it's not arrived safely, that means a transport layer responsibility to ask the sender to send it again, right? So, make sure you arrive, guaranteeing, providing quality service. Unlike other layer, no needs to share information among themselves to make a decision. So issues of a network layer is routing, how to select best route through network is very tricky. But in this case, we're gonna just focusing on the um, shortest path. And the congestion control, problem, too much traffic, addressing how to identify nodes and the host and node using IP address. When you get to the data link layer, you use a MAC address, right? So internetworking, how packets, delivery packet across a network of different networks. So routes are computed once, programmed into switches and routing table. Routes do not, change. This is a static route. A static means it does not change. It's a routes are computed once, programmed into switches and routing table. It's always uses that same route, whether it's a congested or not. It's suitable for the network topology, and when there's not much traffic, changes in pattern, and that is really good for it. And for the source routing, sender decide on routes for each packet, and the route is specified when in the header. Basically, the source at the beginning of the route determine the path for rest of the network. So the path to the destination. That means each node in the topology needs to have a total picture of the network, current network, right? So it's suitable when sender wants to send certain route for testing to avoid other routes in competition network. It causes extra field in the packet header because you need to send this its own node status to everyone. A processing burden because each node send the statuses of its own node to everyone. So, updating and under status is very challenging too. So, it's a flooding is used to broadcast topology to all know the flood. It doesn't matter. You just send it out the packets, and it will distribute to everybody, like in flooding. Either it doesn't have any intelligence. It's very simple. Does not need no network information or routing table. It reverse for fairly prone network. Its shortest path is always found through flooding. You just send it, then you'll be bombarded with number of packets in the network. It's in the network. It's throughout the network. Okay. Source node broadcast packets to all the neighbors. Those broadcast to neighbors again. There's various method for prevent infinite number of packets, which means if you go through, certain number of hop, if it, make the packet destroyed, things like that, and called the hop count. Okay. And alternatively, it broadcasts only the spanning tree. Spanning tree is a subset of a connectivity graph, connect all the nodes with no cycle. Spanning tree must be maintained and updated somehow. So flooding is something like this. Flooding means A send the packets to everybody, all the node. Then this node, generate it again, send it out to all the link. It does not send back to the link it came from, but send it out to all the link going out. And also the packet 3 and going out from this node. Okay, and when this node receives, you send it out packet 3. As you can see, it receives a lot of duplicate packets. Okay, as you can see, it receives a lot of duplicate packets. So that's a big problem. It does flood. This is only a 7-node network. For example, if there's a 50 node or a 70 node, all of this flooding is eat up the bandwidth. It's what we call it as overhead, right? It just eat up the bandwidth, and its efficiency really drags it down. So this is flooding, but the flooding along the spanning tree is much more efficient. Okay, so once A sends it out to all the nodes, here, it sends it out to all the outgoing node, right? Right. If it's all the outgoing node here, so if it's received, is a node is received, it does not send it out to everyone. It's only send it out to where the node has not received the uh, uh, from node A. Okay, so flooding only the spanning tree. What does this mean? That it receives only once, right? This is like a tree, right? Yeah, Christmas is coming soon. So this is like a tree. So it receives a packet only once. Okay. So random routing is just outgoing link of packet chosen randomly. You send it out randomly with set of probability. So it sends out, probably could be based upon link rate or the fixed link info distributed uniformly. So for example, random rate is, let's say A send it out to, this link. It does not send it out to this link. How it chooses, probably randomness of sending out. So it sends out to this one, then this one distribute, send it out to this one. You may not send it out to this one. It just, goes around. Okay. But what is relying on is eventually that the packet will be arrived at every node. Okay, that's what's relying on. Eventually, your packet will arrive at every node. Okay, but this is not an optimal way of routing. Okay, so all those. Remember, there's a random routing, flooding. Okay, source routing, a static routing, and shortest path algorithm, particularly using the source routing. Okay, it's not using this. It could using the static routing initially, but it's most cases using the static routing, and not in flooding or random routing or the hot potato. Once you get rid of the packet quickly as possible, once it receives, send it out to the any link. So that's a hot potato. Once you have a hot potato, you don't want to keep it, right? It's too hot. You just send it out. Okay. So another routing is least cost routing or shortest distance routing. This is where it comes to play, is that the shortest path routing, it can be a least cost, whatever the cost of the link is the smallest, or it can be the shortest distance routing. Okay. So you need to have assume the knowledge of an entire network. What does that mean is you need to have a total picture. Okay. Total picture of the network. And network is represented by graph of the nodes and link. Each link has assigned a link, or generally the cost. Each link has the cost. Okay, cost, it depends on a lot of different functions. It can be a distance, right? It can be the delay. Delay different. It doesn't matter how long the distance. Delay means that's related to how much load, how much traffic being in that link. Okay, so how much, also the what will be the capacity, how big the tunnel, And does it have a lot of fiber optics in there, or maybe only one fiber optic in there? So what is the capacity? So it generates the cost. It's more expensive if there are a lot of traffic going through it. Is it used more used? It's like demand and supply, right? Like let's say there is a national Korea football day, right? And it's the Korean footballs, 축구, they're playing against, for example, Germany. So it's a World Cup, for example. So a lot of people wants the ticket, right? A lot of people wants to come. There's a huge demand, but there's a limited supply. That means the cost going to go up tremendously, right? So let's say they're playing against maybe a lower level team. Korea to play against a lower level team. Nobody wants to come. There's huge supply, but the less demand, the cost will go down. They need to sell it somehow, right? It's better to fill the stadium with a no than having a no people in the stadium. They try to reduce cost. It's all demand and supply. So objective is to find route between source and destination with the smallest total length, or least cost. Is two-way, is being used. This is where the shortest path algorithm comes into play. There's a Dijkstra algorithm. This is called link state routing protocol. And there's a Bellman-Ford, is a vector distance routing protocol. Those two are very famous routing protocols, okay? A link state routing protocol is being used. Those are two very widely used algorithms, okay? So here's a network, a graph. Here's a spreading tree representing least cost route from A to all the node, okay? All the node. This is the cheapest way to get to all the nodes. If node A wants to send it to this node here, the cost will be 3. This is the cheapest way. This is a spanning tree. Remember we went over it last time? So this is the cheapest way to get there, okay? So when you take a look at the Dijkstra algorithm, let's study that. Each node has a label xy. So x is the previous node, and y is the distance from source node along the best known path. It's a distance, okay? Distance. This is x is the previous node, y is the distance. So up to that time. So label is either tentative or permanent. It becomes permanent when it represents the shortest possible path from the source node. Okay, it tries multiple times, but it picks the shortest possible path from the source. Algorithm proceed to find shortest path from the source to another nodes in increasing order distance. Okay. Proceed with the in a stage by the stage K a stage. I mean, there are a number of different stages. Okay, you try with the because this is possible here. It has to be more of a source routing. Okay, which means is the routing protocol provides cost and and the node current status to distribute to everybody. So every single node in the network have a same topology and cost information. So therefore, every node or each node can perform source routing using a first shortest path using Dijkstra and the Bellman-Ford algorithm. Okay. Each preceding stage, by stage K, we'll find the K shortest path from the source node. Those nodes include set M. And next stage, shortest path is found the nodes not in M. This node is added to M. At end, when M includes all nodes, result is the shortest path spanning tree with the root source node. You might not understand what I'm saying at this time, but I have a graphical display and next few slides and help you understand what I'm talking about here. For in directional algorithm, let's say one is a source node, Cij distance, cost, C means cost between node I and J. M is a set of a permanent node found so far. XY node label means X means the previous node, Y means the distance from the source to this node. Okay. Okay. So basically what happened is initialize all the label to dash and infinity because nothing is assigned, and no one to set one because remember here source node is a one here. From last node add to M, update the label and neighbor nodes. If a shortest distance can be found, change node label to shortest route. Okay. Among the nodes not currently in M, choose the node with the smallest distance is label. Make this node permanent and add to M. And you repeat this includes all the nodes. Okay, among the nodes not currently in M, choose the node with the smallest distance. I'm not talking about the largest, it's the smallest distance in the label. Make this permanent and you add to M. You keep adding until you include all the nodes, okay? So let's say graphical version of here's here are the nodes, okay? And this is number one, it's indicated here. So remember this right here, right? If this one node label here, previous node distance from the source is this node, okay? So its source to each node is 0, you dash. There's no previous node, right? And all of this set at the infinity. So it hasn't really started yet. Because when you look at this node, node number 2, the previous node is 1, and the distance is 2. What is the shortest way to get to, 1 is 2, right? For node number 3 is the previous node is 1. It's not this one. It's not this one. Previous node is 1 here, right? The cost is 5. Okay. And it does all the 1/2 first. Update label nodes from the node 1. Node 1. Whoever connect directly to the node 1, right? So in this 4 is connected to the number 1 here. And 1 means the previous node is 1, cost is 1. Okay? Okay. So this is what's it look like from the 1/2. Okay. So from this one, it has a 1-1 here, and there's no other way to get to 1. So, you add this node here. Okay. Choose node 4 to add to M is because 1, 4, makes a 4 permanent. Okay. From here, you choose this one. Okay. Then you expand. Okay. Expand. Okay. So in this case, the next node is previous node is 4. And 4 here too, and the cost is 4. 3 plus 1 plus 3 is 4, right? And over here, previous node is 4. 2 is 1 plus 1 equals 2. How come this does not change? Because previous node 1 is 2 is the least cost. Because if it's a 4 here, let's say this is 4 because the 4 is attached to directly, the cost will be 3, right? 2 plus 1 is 3, which is higher. In this case, it's better to keep 1-2 because this one has the least cost, right? So and you find out that after that, that this is, a least cost because there is no way to, choose 2 because to add to 1, 4 to make the 2 permanent. Okay. From update label neighbor node. Okay. The update to a label node. it's a neighbor node. In this case, is this is a 2 with 5. They add a 2 here, then the 5. 5 makes a permanent because there's no shortest path to get there. It's a 5 makes a permanent 4-2. Okay. From this one, it updates. It update here. The previous node from 4 is 5 is a previous node. The cost is 3. 1, 2, 3. Why this is not 1 comma 5? Because 5 is a higher cost than 3, right? 5 is higher cost than 3, so it's better to keep 5 comma 3 because we're looking at the least cost, right? And over here is 5 comma 4 means a 5 here. 2, 1, 1 here is a 4. Okay. Okay, it's 4. So that's we're left off. So you add this one, you evaluated this one, you can evaluate this one, you can evaluate this one. This is showed as 3. Okay, the 3 makes it permanent. Okay, now next step, update the label at node 6. Okay, so from node 6, it looks at the where is it? It's node 6. It's better to go 5. Here is a 4. If you go here, like 5 here and 5 here, that's 10. It's higher. Over here 3, then 5, 3, and 2, that's 10 too. So that is higher as well. In this way, is the least cost is a 2, 1, 1. So 5 is least cost. So at the end, it shows the spanning tree representing the least cost. So 2, 3, 1 here, 1, 2 here, 5, go through the, it needs to go through the 5 to get the least cost. 6, you need to go through the 5. 5 needs to go through the 4. Cost is 2, 4 it comes to 1. This is the least cost. So when you look at the table algorithm, so algorithm table, and for m equals 1, then node 1, 2, the 1, 5, or 1, 1. This is what we looked at. Remember in the beginning? So when we add the 4, that means 1, 2, 4, 4, 1, 1, or 4, 2, and dash infinity here. Okay, then 1, 4, 2, you add this 4, 2 over here. 1, 4, 2, 5, you add it here. This is what we want over. Okay, then you want 4, 1, 4, 2, 5, 3, this is it, and 1, 4, 2, 5, 3, 6. These are the node information. Okay, for the shortest path. So it knows which previous node it will be. It needs to previous node means packet will come from 1. For the 2, packet will come from 1. Packet will come from 5 for node 3. The cost is 3. Packet is coming from 1 for 4 and things like that. Okay. Hopefully this helps. This is the shortest path, basically a spanning tree. Okay. Okay, so let's move on to Bellman-Ford. Is a Bellman-Ford's Bellman optimal discipline? I believe the Dijkstra algorithm is more popular than Bellman-Ford. Personally, because its path is if path is optimal, any segment between 2 nodes along this path must be optimal between those 2 nodes. Algorithm proceeds to find the shortest path from source nodes to all the nodes in increasing order to the number of hops, and find the shortest path of 1 hop and shortest path of 2 hops, and stops when next iteration does not change anything. Okay, so it precedes the iteration. Each node is responsible for updating its own label at each iteration. This is somewhat different from Dijkstra, right? In this case, is each node is responsible for updating its own. It's usually the neighbors for the Dijkstra, right? So node looks at the route through all these neighbors and choose the neighbor with the shortest route, ends when no more changes. The route result is the shortest path spanning tree with the root at the source node. Okay. So initialize all node labels to dash infinity, except all source node is a dash 0. Each node calculates a route through all neighbors. And choose the shortest path and update node label if necessary. Then iterate. Each node calculates a route through all neighbor. Okay. So what happened is that initialize a node is the same as in a Dijkstra algorithm. Okay. So what happened is each node updates it. Each node is not like a neighbor node here, but in this case, each node calculates a route through all neighbors. Choose the shortest path, updates in neighbor if necessary. So in this case is this one. It's all of this in updates it. What is the shortest path to the one? Is there anything next to it? It looks at all the next. So in this case is a 1, which is 2 here. 3 is a 1, and the 1 here, and 5. 4 is a 1, 1 here, and the 1 here is a 1, and it's a dash infinity. Okay. So it makes an iteration based upon that. Iteration 2, because iteration 1 is this. Iteration 2 is it looks at the neighbor and see which is the shortest. Right now for 3, you understand neighbor has 1 1 here, neighbor has a 4 2 here, and a 1 2. So you will determine which path is the shortest. Okay, which path is the shortest. So in this case is it's not the 5, it's not the 5 through here, it's go through the 4 is the shortest. The 4 here and the 1 1 here is the shortest. Okay. The 5, then after that it's a 5 3 and 5 4. And 5 3 is a 1 1 here, 3 here, and 5 4 is a 1 1 4 2 5 4. So you looks at the each both of them. So what will be the best way? Because this one has 1 2, this is 1 1 4 2. Best way to the the 1. You realize that the 5 is least cost because 5 has a 1 1 1, which is a 3. 6 has a 2 2 2 1 1, which is 4. Okay. So there's no change. If anything needs to be changed, if there's no change, it stops there. Okay. So no label define the shortest path training tree, and it looked like initially. I want you to go through the table after this presentation. As you can see, it's different. So iteration node 2, node 3, node 4, node 5, node 6 is at the infinity. These are the value at the first iteration, second iteration, is all the nodes and updating it, right? This is third iteration and fourth iteration, okay? So there are other shortest path algorithm, but this is more a fundamental shortest path algorithm. Each one of you should know. Okay, so still a lot of in the industry, in commercial, still Dijkstra algorithm has been used. Okay, so that's it for the spanning tree. Thank you for listening. I really appreciate that, and I hope you have a great day. Okay.